this video, we're going to talk about the transformer.
So when we talk about the transformer, it's actually good to talk about the historical context
Of which Faraday made his original discovery that a time-changing magnetic flux causes an EMF.
So what he had here was this induction ring set up. And what this induction ring consisted of, was a battery with a switch here with a coil wrapped around a soft iron ring. What happens is that when we close the switch here, only at the time when he closed the switch would he notice there would be a voltage that would register on the galvanometer, that would measure a slight current. So he only noticed this though when he opened or closed it, when there was this change in the magnetic flux.
And that's pretty important to what we're going to study today.
And this induction ring, was a transformer.
So a transformer will be a device that we're going to talk about that increases or decreases AC voltage, alternating voltage, right? So the way that a transformer works is that you have this primary coil of wire attached to some voltage source. This primary coil of wire, when that voltage source goes through it, it's going to generate a magnetic field. That magnetic field is going to align the magnetic domains within the soft iron core such that this magnetic field will be carried all the way throughout, and that magnetic field will go through the secondary coil of wire. When it goes through that secondary coil of wire and it changes, that secondary coil of wire will have a voltage, an EMF. So what happens is when you have an alternating source, you have a continually changing magnetic field through this soft iron core, and that causes an alternating voltage on this secondary coil. If we look at what the EMF generated by the primary coil is, we see here, we're using Faraday's law, that's just the number of turns in the coil times the time change in the magnetic flux. Same thing with the secondary coil. Since this iron core doesn't change, the magnetic flux through the iron core is the same, they're both identical. So we can actually solve for the magnetic flux and set them equal to each other. When we do that, we end up with the EMF in the primary coil divided by its number of turns is equal to the EMF in the secondary coil divided by the number of turns in that coil. That's really helpful. Then I'm going to replace, you see I've replaced the EMFs with the voltage. We get the ratio of the voltages between the coils is equal to the number of turns, the ratio of the number of turns in the coils. What this leads to is that we get a couple of different transformers. We can have a step-up transformer. What this means is that if the number of turns in the secondary coil is greater than the number of turns in the primary coil, that we actually end up with an increase in the voltage. The voltage in the secondary coil is going to be higher than the voltage in the primary coil. A step-down transformer is the other way, We have fewer turns in the secondary coil, so that leads to a lower voltage generated in that secondary coil. This is really helpful, when we want to manipulate the voltage in a circuit. So, this step-up transformer, that might bother some of you. Some of you may be wondering, doesn't that violate the law of conservation of energy? If we're increasing the voltage, that increases the amount of charge being carried, the amount of energy being carried per charge. Remember, voltage is, another way to think of voltage is the energy that's being carried per charge. What's actually happening here, is that it's not being violated because what we have is that the power input is equal to the power output. When that's completely true, there are no heat losses, we have an ideal transformer, 100% efficient transformer. We're always going to lose some power in the power output, so the power output will always be less. But we can still have a stepped-up voltage, at the cost of whatever the current is. So what we get is that the primary power is equal to the secondary power for an ideal transformer. We substitute our equation for power, voltage times current, and we end up with this inverse ratio between the two. That the ratio of the voltage of the primary coil to the secondary coil is equal to the ratio of the current in the secondary coil to the primary coil. It's so important to remember this one right here. It's all about the powers being equal between the two. Also, when you change the voltage through one of the coils, you'll most likely be changing the current through it as well. So we always want to talk about this in terms of power, okay? That's the easiest way to think of this, and then solve for the voltages and currents. So we have this first example here. We have a 120 volt AC wall outlet connected to a small appliance with a resistance of 2 ohms. So apparently this appliance has a little transformer in it. It's going to step the voltage down. How do we know it's a step down transformer? Well, we look at the image here, we see in the primary coil we have 1,000 turns, and in the secondary coil we have 50 turns. If the number of turns in the secondary coil is less than that of the primary coil, we end up with a step down transformer. That is our evidence. So then, we want to solve for the amount of voltage that the secondary coil has. When we do that, we set up our ratios, we solve for the secondary voltage, and we get 6 volts. Part C asks us to solve for the current that the device uses. If the current in the primary coil is 150 milliamps, what that allows us to do is to solve for the power in the primary coil. If we assume this is an ideal transformer as we are told, we always got to make sure we follow our assumptions here, then the power from the primary coil is going to be equal to the power in the secondary coil. In that case, the current through the secondary coil, when we solve for it, will be 3 amps. I've given you this resistance here, and you can also double check that the 6 volts and 2 ohms there produce 3 amps as well. However, let's talk about real transformers, okay? The power in the secondary coil, like I said before, is always going to be less than the power of the primary coil. The efficiency will just be the ratio of the output divided by the input, which is the primary, and the power in the secondary coil divided by the power in the primary coil. Modern transformers are typically 99% efficient, okay? Here are the reasons for losses in real transformers, okay? Obviously there's heat loss due to the resistance of the wires. The main method for reducing power loss here is to reduce the current, all right, that you are using in your transformer. Also, okay, not all of the magnetic flux makes it into the secondary coil. Okay, it's not linked completely. Another issue is that the core is going to warm up as a result of cycles of the flux changes with the magnetic field going back and forth. Okay, that does mean that there's changes in the domains and there is some movement there. Okay, and that movement, all right, heats things up. And when you heat things up, you can never really return. You're sort of changing the material, okay? And when you do that, that heating up, all right, you're going to lose energy. Also, there are small currents that are induced in the core, these eddy currents, all right? When you have a magnetic field going through a large conductor like an iron core, all right, you're going to induce little currents in there. Now, we haven't talked about eddy currents. We are going to talk about them when we do some review. All right, but they're just little circular currents within the metal. Those little circular currents end up heating up the iron core. So what happens is that you can section off the iron core and put little layers of lamination and sort of layer it. So you have one layer of iron, one layer of lamination, and you just keep layering it like that. And what that helps to do is to prevent the development of these eddy currents. All right, we'll talk about that in another class. There are some good diagrams of this in your textbook, section 5.8. So here we have another transformer example. All right, we have a alternating voltage source that produces 240 volts RMS. The number of turns there is 1,000 turns in the primary coil, 50 turns in the secondary coil. So if we calculate the voltage, all right, from the secondary coil, it's going to end up being 12 volts. All right, that's just from the ratios. I'll let you figure that one out. The current, okay, in the secondary coil, well, the total resistance, we're going to have to add the 0.2 from the coil and 4 ohms from the lamp that we have. That's going to be equal to 4.2 ohms. And when we solve for that current, we can get 2.86 amps. Again, you can write the work down for this to help you out, right? So if we solve for the power used by each of these, okay, each is going to be using 2.86 amps. I like to use, in this case, power is equal to current squared times the resistance. And so for the light bulb, all right,
power that's going to end up being used is going to be equal to 32.7 watts. And for the coil, due to its 0.2 ohms worth of resistance, the power that ends up being dissipated is 1.6 watts. So the total power taken from the main supply, okay, if we consider this, all right, is going to be equal to 36 watts. All right, I get that because this is 240 volts times 0.15 amps, 150 milliamps. And the total power used on the other side, okay, is 34.3 watts when we add those up. And here we can figure out the efficiency of the transformer as 95%. All right? The rest of this we will cover in class. We're going to talk about power transmission and the health issues associated with power transmission in high voltage lines. And we'll also do an example in class for this. So if you've completed this, I would highly recommend finishing the rest of the practice we had on Faraday's law and Lenz's law. Those solutions will be posted soon. And I'll see you guys next week.